So I want you to start by using your imagination a little bit. Like, you've just joined a fairly well-established company. They're doing well. They're making enough to get by. In fact, they're past that. Like, they're making more than enough to get by. They're absolutely thriving. They've built things in a modular way, scalable, there's microservices. There's a mix of half a dozen different languages on the platform. They're using PHP for things that PHP is good for, Python for things that Python is good for. Like, they're using the right tool for the job. You can't wait to get stuck in and start contributing. It's a great job. You're really excited. So on your first day, you go in, you sit down, and there are no tests. Zero, none, nada. Not a single test for any service in this infrastructure. Your co-workers say, oh, don't worry about it, Michael. Like, it's fine. Just start making changes. We will notice if you break something. But how familiar does that sound? It's down to you to convince them that there's a better way to handle this problem. It's down to you to say, look, it may be working, you may be making money, but we need to solve this to have any confidence that we're not breaking things with our changes. Now I want you to imagine that there's a tool that will help you exploit that code base, understand it, refactor code without fear. Doesn't that sound like I'm dreaming? But this tool exists. It's available today. It will take a little bit of work from you, but you can sit down, you can go back to the office, you can go home, and you can start adding some tests that provide confidence in the changes that you make. Hello, I'm Michael. I'm Heap on Twitter if you want to say nice things about the talk. If you want to say bad things, do not put that on the internet, please. And I work for a company called Nexmo. Just out of interest, how many of you have heard of Nexmo before this talk? A couple of hands, that's good. And at Nexmo, I get to play with really cool things, like going on a phone call with someone else, me speaking one language, them hearing another, like real-time translation on a phone call. Works well with Spanish, Italian, German, Dutch, not so much. It's quite a tough language for automatic translation. But today's talk is not about Nexmo. It's about the time that I worked on this awesome system. And this thing processed terabytes and terabytes of data per day. It included a multi-petabyte Hadoop cluster that archived information, and it had several internal but critical systems that were about 7 years old. Things like authentication, things like billing. What we wanted to do, we wanted to go in. I think PHP 5.3 was coming to end of life and we wanted to upgrade. But we had no confidence that the change that we made wouldn't break things. Somehow, we had to write some tests to gain confidence that the changes we make were safe. Which brings us to today. Today I'm going to talk about the tools and techniques that we use to successfully test and upgrade that system. We'll start off by covering what characterization tests are and how they can be useful to you. We'll show a few examples of the tests that we wrote to make sure that things didn't break. And then we'll cover a few tools that have come out since that I wish had existed when I had to do this. But I want to start by asking, like, for you, what defines legacy code? Like, just shout. What is legacy code?
No tests.
No tests.
Code from yesterday.
Code from yesterday, yes. I can sympathize with that one. Code you didn't write. Yeah, I can sympathize with that one too.
Code that provides the livelihood of the business and all its developers.
Interesting. I don't normally get that one, so the answer was code that provides the likelihood of the business and all of its developers. So the most common definition for legacy code is code without tests, and this comes from working effectively with legacy code by Michael Feathers, which I just happen to know that Robert is reading at the minute. And whilst this is true for some projects, this definition never really sat right with me. And in fact, it's the other definition that really does. This is by J.B. Rainsberger, and I've got the hashtag over his name. But this is a perfect definition for me, because legacy code is valuable code. It's code that the business depends on, that developers depend on. It's code that we want to change, but we're afraid that we'll break it because it's is providing value to the business. And by this definition, the code that we wanted to change was definitely legacy code. It had been running for years for the business. It was running the billing system. It was definitely making money. It was providing authentication services. And it was full of hacks. It used singletons everywhere. And of course, it had no tests. But they delivered value every single day. And I was worried about making changes to them. I was worried, what if I make a change and I break something? And this actually is the best case scenario. Because if you break something, you're going to find out quickly. Your error logs are going to be filled up. Your customers will start complaining. People will report it. The dangerous one is, what if I make a change and I change some behavior? What if I change some behavior without realizing it, and we notice 3-6 months down the line, we've got 6 months of inaccurate data, or 6 months of invalid billing. We may have overcharged, we may have undercharged. This is worse a lot of the time, as there are no errors, just subtly different behavior. And whenever we make a change to code, we are either making an intended change or an unintended change. And intended changes are fine. If you deliberately made the change to the behavior, a change to the code, and it now behaves the way that you expect, you may fix the bug, you may have added a new feature, that's fine. You expect a change in behavior, you can go in, you can update any tests that may be failing, or you can write a new test to cover the new behavior. The issues arise when you make an unintended change to the code, because unintended changes aren't okay, they're side effects. And if a change is unintended, it shows that there's been a misunderstanding about how the code actually works. It's led to a change in behavior that you weren't expecting. And in this situation, you can't change the test because you didn't intend to change the behavior. So instead, you have to go back in, fix your code until it does what you want without having any side effects. But Michael, I hear you say, there weren't any tests. Like, how will I find out if the change that I made had any unintended side effects? And that's a good point. But fortunately, we have the source code to look at. So we can go in and take a look at what it's supposed to do to get some ideas about what to look at after we've made the changes. And we don't know what the code is supposed to do, just what it currently does. But as it turns out, that's a great starting point. You write tests documenting what the code currently does, and these are known as characterization tests. Characterization tests act as a change protector in a way that they protect code from unintended changes. And we've got this class. Reading through it, it's a little bit messy, but we can kind of work out that it's used to calculate sales commission. It's got a single method. It takes a single parameter. There are 3 paths through the method, which means that we need to write 3 tests, at least 3 tests. So let's take a look at the first one. And we can identify that it triggers when the number of sales is less than or equal to 1,000. So let's write a test for that. And you can use any testing framework that you like. Characterization tests don't need a specific tool set. Here I'm using PHP unit, and I write a test to capture what happens when we pass in a value that's under 1,000. A value of 1,000, sorry. And there are 2 important things to note in this test. The first is the test name. Like, we don't know what we're testing yet. We can't say test that the output is 20% commission when we pass in 1,000. Like, we don't know that that's the behavior. So we just call it test X. Like, we don't know what we're testing, just give it a name so it runs. And the second is that we're asserting that it will return null. By reading the code, it's a fairly safe assumption that it will return a number. So if we assert against null, we expect it to fail and tell us the actual output. If you run this test and it passes, then you need to take another look and change the assertion value to false or true or 42 or whatever you want. You just need the test to fail initially. So as it turns out, our test returns 200 for an input of 1,000. And by reading the code, we understand that for values less than or equal to 1,000, they're paid 20% commission. So we can update our test name. We can say, test that sales less than or equal to 1,000 pay 20% commission. Normally, we'd had a few more tests here, perhaps with a low number like 1, somewhere in the middle like 658, one right on the boundary like 999. But let's move on to the next statement. And this one looks a little bit scarier. But by reading the code, we can work out that it triggers if our sales are less than or equal to 2,000. Let's add a test for this. Again, we call it test X, but this time we'll pass in 2,000 as our value. And looking at our test output, we see that they're expecting 500 commission for an input of 2,000. Here, I would have made an assumption that if less than or equal to 1,000 is 20%, that this one will be 25%. But that's an assumption, so let's update our tests, add the actual value from passing in 2,000, and add another test. We call it test X because we don't know what we're testing. And this time we pass in 1,600, which is above 1,000 but below 2,000. And here I think it's going to come back at 400, just guessing based on the data that I've got. But when I run the test, my assumption doesn't hold. For 1,600, the commission paid is 380. So we fill in the test name, the expected value, and we start adding more tests. We might pass in 1,200, 1,317. Just keep adding tests until you're comfortable that you've got enough coverage for that code path. And once we're happy with the coverage, we can add tests for the final input. Based on our boundary inspection, we can see that this is applied for any values over 2,000. Choose a few values over 2,000. I'd probably choose 2,000, 2001, 9,999, 42 million. Because the boundary is over 2,000, it can be any value above that. Just choose a few values, write some tests, and your job is done. Here we have 13 tests that characterize the behavior of this method. There is no correct number of tests. Just write as many as you feel comfortable with. The more the better, in my opinion, but given the trade-off that they take time to write, they take time to run, and they take time to maintain. You can even throw in some tests that you'd expect to fail, like entering a negative number, because I'm sure your salespeople don't go out and hand people money. They usually go out to take money in. But here we write a test, the commission on minus 123 should throw an exception or return false or return 0. But actually it returns minus 24.6. And this is a great way to expose assumptions in your system. It's really tempting to add a quick check here to say, make sure that the input is above 0 and throw an exception if not. But there's one thing that you definitely shouldn't do when you're writing characterization tests, and that is do not change the code. We write our test, we capture the behavior, and then we move on. It sounds a bit crazy, doesn't it? We know that you shouldn't be able to have negative sales commission, but sadly this kind of thing happens all the time. Because once you make code publicly available, you make a commitment that its behavior won't change without prior notification. Once the code's made public, the original requirements are forgotten. Right and wrong don't matter anymore. The only thing that matters is how it currently behaves. And once you ship a system, that's what you have to support. Once you ship, customers might be relying on that behavior, whether you intended it or whether you didn't. Once you ship, you've entered into a contract with your consumers that things won't change on them unexpectedly. And they could be actual customers, they could be internal customers, they could be the person sat next to you at work. Once you ship, that's a contract that you've got to honor. And just to really drive this point home, do not change the code. Because having these tests helps developers working with legacy code because they can make sure that their code still behaves the same way after they've made changes. The test isn't interested in what the rest of the code does or why it works that way. They only care that the parts of the system that they monitor haven't changed. They care that a developer hasn't gone in and unintentionally changed the behavior of the system. Because in legacy code, different is dangerous. And these tests provide an invaluable notification system for when things change. So what's the minimum number of tests? That depends on your application. There's a great technique called equivalence partitioning, and it looks at the code and it provides one test per boundary. Imagine that you're validating that a month number is accurate. There are 3 possible cases. Either it's less than 1, in which case it fails. It's between 1 and 12, in which case it passes. Or it's above 12, in which case it fails. And that's equivalence partitioning at a basic level. You look at the edges of your system, and you pass in values that are just below the edge, just above the edge, and on the edge. If you want to read more about equivalence partitioning, the Wikipedia article is surprisingly easy to read. Like, it doesn't go too much into the maths or anything like that, so I can recommend having a look at it. So, we're 40 slides in, and we've barely mentioned Behat. But hopefully now we all understand what a characterization test is, how to come up with the test cases for our code, and most importantly, that we're only documenting how the code behaves. Like, we're not changing it. And that last point is, like, it's really hard to overstate. When I was working on that system, we were writing these tests, and I worked with one team member, and he insisted that our memcache library that we shared across all of our different microservices was badly designed. He said, look, when we can't connect to memcache, it returns null instead of throwing an exception. That means that every time I want to use a reference to memcache, I've got to check if it's null before I can perform an operation. And I said, yep, I agree, that's a bad design. I said, cool, I'm going to update it to throw an exception. No, you can't do that, because if you do that, and we deploy a new version of our billing system, and it can't talk to memcache, we won't bill anymore. If we update it and we deploy a new authentication system, and it can't talk to memcache, which is, it's a side effect. Like, we did a little bit of caching for performance reasons, but if memcache was offline, I'd rather just hit the database every time. It might be a little bit slower, but at least people can still do what they need to do. Like, he couldn't appreciate that making what seemed like a fairly small, trivial change will break half a dozen other services. Now, when you're working on the real-world system, the first thing to do is identify pinch points in the application. That is, what are the entry and exit points that we can test to provide coverage for the largest amount of code with the fewest tests. In the earlier example, we saw that we were just testing a specific method because it was nice and self-contained, but most applications aren't like that. For most applications, your best pinch point is the HTTP layer. It turns out this is a fantastic pinch point in almost every application because PHP is designed to talk HTTP in, HTTP out. You have a well-defined input and a well-defined output, and it doesn't matter how the code works, or in fact, it doesn't even matter what language it's written in. And that's what makes HTTP the perfect pinch point for capturing the behavior of web-based applications. You don't care how it works, so long as when you send a specific request, you get a specific response. And if we're choosing HTTP as our pinch point, why not choose Behat? Because what's better to capture a system's behavior than a behavior-driven design tool? We just so happen to have Behat in the PHP world, which allows us to capture business requirements in a human-readable language. That language is called Gherkin, and it looks like this. And the human-readable steps, which translate to programmatic instructions underneath, and because they translate to code, you can do pretty much anything you can imagine. They follow a specific format of given, there is a prerequisite, when an action is performed, then I make an assertion about the current state. And this one is pretty good as far as decoupling your business logic from a specific implementation goes. It doesn't need to know how to add things to a basket or how to inspect the basket state, just that those are the requirements. Now, what I'm going to show you today would make a serious BDD tester cry, but I'm firmly in the pragmatism over dogmatism camp. These techniques allowed a team of developers and QA staff to test using a common tool. Some services were PHP, some were Scala, some were C++. And the team wrote half a dozen different languages across all of the developers. But none of that mattered, thanks to the abstractions of HTTP, Behat, and Gherkin. The first thing to do is install Behat with Composer and initialize a folder structure. Once you've done that, it's time to start writing tests. We're going to start off by writing tests for a HTTP API. So, back to the beginning. We've just started a new job. We've inherited all these services. And you look at the auth service, and it accepts a username and an API key, and it returns whether it's valid or not. And everyone interacts with it via HTTPS, meaning that you have the ideal pinch point to test against. And now, so long as the service behaves identically to people consuming the HTTP API, it doesn't matter how the internals of the service works. You can refactor, you can change it, you can rewrite it in a new language. All they care about is the public contract that they're consuming. And it's a really simple authentication service. It takes a username and an API key, and it returns the authenticated user's name or an error. This is the entire auth service. There's no database, it's just an array with 2 people in it. Let's see how many code paths there are through there. It looks like there are only 2 inputs, the username and the API key. And there are 5 potential exit points. The output and error functions, they set a content type header, JSON encode the payload, and then stop the script execution. And this gives us an outline of all the tests that we need to write. And it's relatively trivial to test all of these conditions by hand, and this is how they've been doing it so far. Anytime there's a change to the auth service, they just go through and test these 5 cases. Someone just sits at their desk over lunch, has a sandwich, types things in, makes sure that it still works. But as the service grows in complexity, the time it takes to test it will increase. And you also can't take someone and stick them in the middle of Jenkins. You can't have a person run their tests continuously every time you make a change. You want to write an automated test. You want to write a test that looks something like this. And the nice thing about testing HTTP is that there's generally no state, so we don't even need the given step. Just when I make a specific request, then I expect a specific response. And this test is definitely coupled to the implementation. It talks about GET requests, response status codes. But in my opinion, whilst pure BDD testers wouldn't like that, I don't think it's too bad. Because I can look at this, I can read the test, and I know exactly what it does. It's coupled to the implementation details. But if I wanted to go and test it by hand, I can look at this test and say, oh, I make a GET request to slash, and I should get 400 back with an error. So that's one test, no username. Moving on to the next test, we can provide a username, so it'll pass that check. But this time it fails as we don't specify an API key. And then we add tests to ensure that we receive errors for invalid usernames and invalid API keys. And then finally, we test our success case. 5 paths through the code, 5 tests. 5, in my opinion, relatively simple tests. Anyone can go in and read these and understand what they're doing. And you can even provide multiple inputs and outputs by building up a table of test values, just like we did with our commission calculator earlier. So here I know that there are 2 valid users for the API. So I can supply an examples block at the bottom of my test, and it will execute once for every value in that table. But those were simple tests. We can test lots of different things with Behat. What if we want to make a post request with some additional headers and a JSON payload, and assert the response code, response headers, and payloads? What if you don't want to assert every item by hand? What if you can make a request and copy and paste it, and you just want to paste that into your test? What if you just want to specify the full JSON document to match against? Or maybe in the response, there's something that you don't control. Maybe I don't know, it returns the current timestamp for some reason. Like you can't go in and mock that out like you would with PHP unit. So instead, you look for patterns. You might want to match a regular expression rather than a specific value. These are best effort tests to capture behavior without changing the code. If we wanted to, we could just ignore that property entirely. But I always like to try and pattern match to gain the most confidence that I haven't broken something. But whatever you do, do not go in and change the code at this point and say, hey, if this special header is set, then always return the same time. Like, then you're making changes without tests. You can't have any confidence that you haven't broken something. Now, all of these steps, unfortunately, are not built into Behat. They belong to a third-party extension, which you install using Composer. That's step one. And then step two is just to add it to your behat.yaml config file so you can start using those steps in your tests. And once you've got that, you can start writing tests just like the ones you saw on the screen. Now, with this job, it wasn't that simple. It wasn't just an array of usernames and API keys. They actually made calls out to external services. So we needed the concept of mocking other HTTP endpoints. The test rest extension does more than just make HTTP requests and inspect the responses. We had a lot of code that looked like this, where when we're authenticating someone, we check their username, but we also check that they've got available credit on the platform before we let them do anything. So here we say, get the balance, and we see the get balance calls another endpoint, localhost 88, billing, check balance. And we were lucky. Everything was routed through localhost port 88. That was just our service discovery mechanism. It was HA proxy. But it meant that we didn't have to edit the code and make the base URL configurable. All we needed to do is make sure that something was running on localhost port 88 that would respond the way that we wanted. We found a solution for that using a tool named Mountebank. This is written in Node.js, not PHP, but it allows you to define HTTP mocks using a HTTP interface. You don't have to define them up front, and this means that you can start the server once and control the mocks in your tests. So you install Mountebank using npm, and once it's installed, you're good to go. There's no config or anything like that. Just make sure that Mountebank is in your path, and it can be run. And by using Mountebank and the mocking steps built into test rest, we can now write tests for code that has external dependencies. Here we test the error case, and you can see we're setting up the HTTP mocks in our test case. You don't have to go off and read other config files and make sure you're running the right things. Like, it's all encapsulated in a single unit. We say, given a mock exists at the path that we're looking for, it will return a 200 with this body. And then we step through the rest of our steps. When we make a request to our auth service, we expect a 403 with an error saying no credit remaining. That's because has credit is false. Updating the success case is as simple as copying the test, updating the mock so that has credit is true rather than false, and changing the expected response body. Now we've got two encapsulated tests that depend on external services that don't have to be running because the test takes care of everything with Mountebank. And this works well when you've got an API. And yes, it's getting a little bit more complicated. It's not just a single endpoint now, like we're starting to get to services that depend on services, but at the heart of it, it's still an API. It's still a system where you can send it JSON and you get JSON back. That's kind of the dream for testing because it's a well-defined interface. But a lot of the time, we don't have that. A lot of the time, we have websites. Behat can do more than just HTTP requests. It has a fantastic integration with the browser automation project called Mink. And using Mink, you can automate a full browser. And you install the Mink extension using Composer, which will provide you with all of the steps needed to test a website. and you'll also need a Mink driver to power the website. There's lots of these available. In this example, I'm using Selenium to drive Google Chrome. I've seen a lot of people have had great success with headless Chrome, but I don't do this enough to need that. I quite like seeing the browser going on the screen myself. So as it's an extension, we need to configure Behat to use it in our behat.yaml file, and this will make lots of additional steps available that we can use in our tests. Take this example test. This is on Wikipedia. We navigate to /wiki main_page, fill out an input named search with BDD, and press search button, and then we expect to see agile software development in the response. As we're driving a real browser, we can run JavaScript, inspect the page's data, CSS, the position of images, anything you can think of. And this can be very useful for automating the testing of things that were previously visually checked. Things where people sat down and said, actually that image is on the right when it should be on the left. You can automate all of that testing as well. And these tests are slow, these tests are brittle, but they're better than a human sitting down and doing them over and over again. The idea behind characterization tests is to provide you with confidence that the changes that you're making don't break things. So you write a test like this, and then you immediately go in and refactor, so you don't need this test anymore. This test will only live for long enough to give you confidence that you haven't broken anything. Now, compared to the lovely example that we saw about red buckets earlier, where everything was expressed as business logic, we seem to be right down in the weeds, like talking about specific fields, specific API endpoints. Let's write some custom steps to wrap up those details into something that the business can understand. Take this test, for example. If we change the name of the search input, we'd have to go in and update every single test that uses the search input. Instead, wouldn't it be great to write something like this? It's only a small change, but it's encapsulated the steps where we type into an input and press the search button. It means that we have to write one line instead of two in every test. And most importantly, if any of the naming changes on our web page or any of the structure, we go in and we change one place in our code. And then all of our tests just start working again magically. If we make that change and run Behat, it'll detect that we're missing a step definition, and it'll offer to generate one for you. And when you initialize a Behat project, it will create an empty feature context. And this feature context is where you can add step definitions specific to that project. So test rest and Mink are also step definitions, but they live in their own feature context that we can pull in with Composer. The feature context is automatically available in your Behat project. If we did want it to be reusable, we'd have to create a library and make it available on Packagist. But as this is for our current project, let's just press 1, add it to the feature context, and hit enter. And Behat will show us a step definition that we can copy and paste into our feature context file. That will give us the building blocks for implementing the step. I'm lazy. I don't like copying and pasting and finding files. So if you run Behat with the append snippets flag, it will automatically add it there for you. And if you open up that file, you'll see a step definition that doesn't do much. It just throws an exception that Behat interprets as a pending test. Not a test failure, just something that you haven't built yet. And the first thing I do is I go into that test and I change the parameters from arg1 to something that's a little bit easier to read, adds a little bit more context. In this case, I rename it to term, because we're searching for a term. And it's still throwing a pending exception. If we run our tests, we get a message saying that we should implement the pending definition. And that sounds like a sensible next step to me. But this is where things start to get a little bit complicated. Because to fill in the form, we have to reuse some of the step definitions from the Mink extension. And to do that, we need access to the Mink context from our feature context. That's what this bit of code does. We can chat about what it actually does after the talk if you like. But for now, let's just add it and keep moving. Now, to run this step, there are two things that we need. We need to type into the search input, and then we need to press the button. And to do this, we need two function calls. The first is fill field, which I found by searching Mink extension for iFillin. And we see that it takes two parameters, the field identifier and the value. So we go back to our feature context and update the step definition, adding a call to the fill field method on the Mink context. Next, we need to click the submit button, which I found by searching for iPress. And we can see that it calls a method called press button that takes a single parameter. Updating our feature definition, we now have a single step that performs both actions. If the name of the input changes or the name of the search button changes, we just come back to this feature definition and update it once. Older versions of Behat, in my opinion, worked a little bit more nicely. You could return a new given or a new when or a new then. You could put the actual human readable string and build up composite steps. But as of Behat 3, that's been removed. So if you start Googling for how to build these steps and see something like return new given, just be aware that it won't work as of Behat 3. So if we run this test again, it passes as expected. Now we have a single step definition that we can use in lots of different scenarios. And this isn't just limited to the Mink context either. We could change our earlier HTTP tests. Remember this one that I wrote to make sure that I could log in successfully? Well, instead of making a GET request to / username Michael, password kangaroos, we can add a custom step that hides our implementation entirely. It's still testing our application at the HTTP level, but if we wanted to refactor our login code to be a post rather than a GET, which we definitely should, or if we wanted to use different parameter names, we don't have to go through and update every single one of our tests. We have a single place that the business logic is defined. And it's a trade-off, because now reading this test, given I log in as Michael with the password kangaroos, I don't actually know how the system handles that anymore. I know that I want to log in, but I can't read this and treat it as documentation, like I could with the last one. The last one was documentation because I could see that to log in, it's a GET request with those two specific parameters. Now, you're starting to get away from the implementation details and have more business-like language. So whilst it's very enticing to go and add all of this business language on top and make the test read nicely, it is a trade-off. It's not a free win. And one final tool to mention is snapshot testing. And this didn't exist in PHP when I was writing all of these characterization tests, but I really wish it did. And this is really popular in the JavaScript world, and it's starting to make its way into the PHP world. I will say that snapshot testing is brittle. It's as brittle as testing a UI. But when you're testing UI, the burden of brittle tests is that when they break, you've got to go in and update the test by hand. You don't have that with snapshot testing, because we didn't write any assertions in the first place. If things change, we can just regenerate our snapshots from the current state. And that don't make much sense, so let's take a look at how it actually works. And the idea behind snapshot testing is that the first time you run a test, it captures the output and just stores it in a snapshot file for future comparisons. So given this test, the first time that we run it, we'll see something like this. It didn't pass because there was no snapshot to compare to. It was incomplete. It ran the code, it captured the output. And if we run the test again, we can see that it passes. So we're happy that the test will fail if we make any changes. And some change comes down, some business requirement, that all IDs now have to start with a queue. So update our code, and when we next run the test, it fails. as the value that we received didn't match our snapshot. And this is a great way to start building up characterization tests when your output is non-trivial, when it'd be a pain to copy and paste all of the output into a test. And this is really useful for things like templating, because a template, given a deterministic set of inputs, should always produce the same output. So you can run your rendering layer, pass in some details, write the resulting HTML to a file, and then you only get alerted if that changes. And if you decide there is an intended change, you can run PHP unit with a --update -snapshots flag, and the snapshot library will overwrite all of the snapshots. If it was an unintended change, then you have some code to fix. Like, don't just keep overwriting your snapshots unless you're sure it's a change that you wanted to make. This is a PHP unit extension, and it's available on GitHub at this URL. Which brings us almost to the end of the talk. Characterization tests are great for gaining confidence in a system that you need to refactor, that are tough to unit test. Behat's a great tool for it, as it focuses you at a high level. You test the system as a consumer without getting into the code. Like if you don't have the code open, the temptation to just add an if statement and say, oh, well, if we're testing, then return this fixed value. Like, it's not there. With Behat, you're at a high level, you're testing at the HTTP level. You're just testing it as a consumer. If your services make external HTTP calls, you can use Mountebank to provide mock responses that can be configured dynamically. If you've got a UI rather than an API, Mink provides everything that you need to test using a browser. And finally, if you want a quick way to test your systems, consider snapshot testing. Run all the tests once to capture the current state, and they'll fail if anything changes in the future. But even with all of these awesome tools available, you know what I hear the most when I say, hey, we should write some tests for this? We don't have time for this. Sure you do, because each time you go through to edit the code, you have to read through it and understand what it does. If you're already spending that time to work out how the code behaves, instead of just saying, yeah, make my change, done, and then going back and having to spend the same time again next time, take that additional time the first time and write a characterization test. It doesn't have to be friendly business language. It can be, when I make a GET request to this with this header, then I expect this response. Not only does it give you a test that you can run to gain confidence, but it gives you documentation. You don't have to read through the code to work out how it behaves. You get a big set of example inputs and outputs, and you can understand the behavior of your system. Spend that time writing characterization tests rather than relearning the code, and you'll soon be net positive. So, where should we start? Write tests for whatever you're working on today. It doesn't have to be an all or nothing job. Just leave the system with better coverage than you found it, and you're good. Once you have test coverage, start refactoring. Use the classic refactoring techniques to help you break down your code into manageable chunks. Inline the code to work out what's actually happening. Use extractor methods. Use other testing tools. Like characterization tests give you the confidence to start making changes, but they're not perfect. They're very brittle. They may not exercise all of the paths through the code, but they are good enough. Use them to cover the most critical parts of your application. And I'm going to leave you with the 4 stages of characterization testing. First, read the code. What does it do? How many paths through the code are there? And equivalence partitioning can help here. Second, characterize your feature. Write some tests to capture the existing behavior. Third, refactor it. Add some unit tests, document the behavior. And then finally, delete your characterization tests. And this is important, because they're a crutch that allow you to refactor and write less brittle tests. They have a non-trivial cost to run and a non-trivial cost to maintain. So don't treat them as a silver bullet. Use them to get to a place where you're no longer afraid to change code, then refactor and add unit tests. This was Behat for characterization tests. I'm Michael. I'm Heap on Twitter. Thank you.